All right, so welcome back to the second part of Lecture 1, Cloud Computer and Big Data Introduction. In the first part, we really covered the foundation of cloud computing so that it has lots of history in the past with high-performance computing systems, technologies, that it was driven by approaches from high-throughput computing. So let's say less centralized systems and more around throughput. Data science will play a big role now in the second part, and we try now bring into perspective why is big data so much interconnected with cloud computing and why this interesting word scalability is so important. We had scalability already in the first part of the lecture where there was computing needs, which goes up and down in a company, in science, before a conference, for instance. When you submit a paper, you want to do some studies, then the computing needs go up. And sometimes in the vacation times, computing needs go low. So in computing, we have the scalability. And then when you think about the users of essentially Angry Birds, starting from complete failure in the beginning and then being extremely successful to millions of users, you have to have an infrastructure that scales and that underneath is somehow scaling with you without, hesitating or basically have the users pay the price for it, to really say the users, now you have to do it completely different. And essentially I'm saying everything you want is under the hood, right? The users essentially should not see any difference if it is the first version of Angry Birds for 100 users or it's Angry Birds for 1 million users. And if you think about the apps that you download today on your apps, devices, whatever it is, Google Play, Android, or basically the Apple way, you essentially have that feeling. You don't know exactly what's behind the scene, where also all the data stored, where is basically the computing done, where is the rendering of good games done. All of this is basically then the idea of this cloud computing fueling apps, fueling many different business applications today as well. So the second part really then drives now more into the big data topic. What is big data and scalability along the way? When you think about big data, it is really a buzzword in science. So I remember the first discussions we had around it when this term came up really at the hype. It was everywhere in the media. It was full with lots of promises. Now we don't have basically any more gigabytes. We go to the terabytes, petabytes. Even this is today for us in science and engineering not a problem anymore. We have no exabytes. Which is really an extremely interesting topic and quite some challenges with it. Some of them I will explore. But in the beginning, it was really a buzzword. You would say, yeah, it's more volume, that's for sure. Then people started really of saying, well, it's not only the volume, so the problem might be the velocity, how quickly come things in. Now, if you think about Facebook, that really comes into the picture, right? Also, billions of users, and if you like, and then someone else should basically see the like in an instant. If you wait an hour and okay, 1 hour and there was one like or two, Facebook wouldn't be popular. So in a way, you need to be really ensure that your system is able to work with a certain amount of velocity of the data coming in and out. And then you could assume in the beginning it was lots of image data where people said, okay, now we have better cameras, so we have much more image data getting bigger, but suddenly the sensors, they had an incredible pace, the sensors on ships, the sensors on satellites. So you would see there's more and more variety. Now, if you think again about online social networks, Netflix, things like this with, basically movies now in streaming services, also the variety of data gets more. And so essentially what I'm going to say here is big data seems like volume oriented, and in a certain way it is. But the problems often is not the volume in itself, it's just the other aspects of it, like veracity or validity. There's lots of noise in the data, as we would call it as machine learning experts. There's lots of data which you don't really need. There's lots of misinformation in the internet, as you know. Everybody is an expert, makes a blog, but in the end, 80% of it is not true. So then there's lots of stuff in the internet which is contributing to big data, which is really be, handled carefully if it is really valid data, so to speak. And this all contributes to the fact that there's now this big data famous V's. So everything with a V word somehow can be related to big data. And I stopped to really name all of them here. But when it comes to the computing and storage size, and maybe a little bit on the analysis that we had already here in the prologue, if you remember down there with the interesting graph bringing all of that together, you can say that these two definitions that you have here is bringing it really a bit in the context of our course, which means you have really data sets that are so difficult to process that you cannot do it with traditional models or traditional applications. When you now put new measurement devices, a time series into MATLAB, it will just collapse. It will never return back to you, or R is the same way. Even scikit-learn has problems. Even though being Python, it's the same problem. It's serial, it's somewhere on your laptop. So you have to use more parallel computing. You have to use, with big data, cloud resources, things which go in parallel to solve these problems, or that offer more memory. So in a way is what is described there. So it is basically the big data is that it cannot be used anymore with conventional methods. And these conventional methods are partly then really these tools here in machine learning and data mining that I just mentioned. But of course, you can transfer that to any other area as well. When you have now big enterprise relationship planning, resource planning systems, customer relationship management with lots of fields, lots of customers that are tracked there. You see more and more data. And when you have just, small laptops or servers which are doing this, they're just overcommitted by this. So this is kind of the definition of big data and the problems and the challenges that you see here. And I just brought you here some concrete example where really you see the volume is not a problem. We in Jülich, for instance, as a supercomputing center, we are not afraid about a petabyte. We're also not afraid about a couple of petabytes. Actually, lots of petabytes is also something we can handle. But you see here one measurement device that is coming up very soon. It's a square kilometer array. And this means 1 petabyte. Yes, okay, that's what we can do. But it will come every 20 seconds, right? So this is a problem. This is a big data challenge. And everybody who has a perfect solution right now here should basically come up and say, hey, I have a solution for this. So this is what the science community is, one of the cutting edge devices where many experts in the whole world are actually not completely sure how we can deal with a vast amount of data. And it should, of course, scale. We want to make use of this data. It should be not just somewhere stored and then archived and never used. A key fraction of the problems we have these days is making data somehow findable, accessible, also interoperable to different devices, reusable, so that people can, use a measurement device that has done by someone and then put it to someone else, to another research group to actually reuse the data. This is a statement in itself called FAIR. And you will find now from the European Commission a strong drive to make every research data fair. But this movement has also reached the business community, that more and more there also the FAIR statements go into the game. And this is something not now just here for astrophysics. This is for weather. It's for the brain sciences, neuroscience. You see, it's basically in the Large Hadron Collider in CERN. It's at the International Space Station. They all more and more have to do open data because it's publicly funded. And with this, you have more and more increasing degrees also of this FAIR data, because really there are political movements now, the G8, for instance, which is strongly backing this up, that we not should reinvent data again, remeasure data again. We rather should share it as human beings and, help the world together. It's easier said than done, right? Because if people spend a hell of a lot of time to do measurements, to do, let's say, ground truths, as we sometimes call it in machine learning. So maybe in remote sensing, a field I work with, you would have per pixel where people analyze this as water, is it a tram, is it a house? This costs a lot of time and a lot of money to invest the time. We have people with, you know, doing the human brain post-mortem analysis of images and label them, saying this is cortical layer 1, this is cortical layer 2. So this takes enormous amount of time. And then, of course, you want on top the analysis. And sharing this amount of time has been traditionally in the past always a little bit a problem, because you spend all the time and then there comes a large research group who is very good in processing in, let's say, have a HPC at their you know, at their disposal and can then quickly analyze the data while you work 10 years in the field to get the data prepared. So this fair statement is really a little bit hard to put in practice. That's what I want to give you along the way. If you go to the medical domain, this is very hard, not only because of the statements I just do now, that the data is very, let's say, hard to generate or basically to measure. In health, you of course face lots of security problems as well. So reusability is a problem that we face in many of our projects when we work with pharma. Pharma has a problem that studies, for instance, done for a specific medicament, for a specific pharmaceutical approach, is usually bound with the patient to this certain study. So you cannot just use this data then for a next study and things like this. So GDPR, this General Data Protection rules, are there for the rescue, and they help a lot with consent, giving, you know, an informed consent that my data might be reduced directly at the beginning, and more hospitals are doing this because then we can pool the data much easier. We can work with the data, create better machine learning models if we share the data, and with this help, of course, much more patients than a normal small hospital could do on its own. So pooling the data, bringing it together has, that's of course a very good return of investment, so to speak. But putting into practice, I give you this on the way, it's not always so easy. Let's put it this way, being 16 years in the field. Now, when it comes now to the idea that when I'm saying big data is inherently not a problem, we will find big archives with petabytes of data. We will soon see archives with exabytes of data. This is all achievable. The problem usually comes when you want to do something with it. You have something where this is usually called a storage hierarchy, where you go from this typical tapes where a lot of capacity exists, extremely cheap, where you can store exabytes, but the access to tapes takes hell a lot of time. So if you want to analyze data, you have to basically say, and if it is in the order amount of petabytes, you have to start basically getting the data today so that you can really properly analyze it in a week. So this is quite inconvenient, right? Because the tape just takes so long to get all your petabytes restored on so-called magnetic disks or on, you know, solid state disks. It doesn't matter really which type of disks, but still these are also very slow. If you think about the capacity of a computing, where we talk about in the course, where you have high performance computing, very, let's say, interesting systems which are very fast, they need this in their caches, in their memory. And of course, it will flow in the register at some point in time. So this is a whole pyramid where it's getting extremely more expensive to the top. Of course, the speed is increasing significantly, but the problem that we have today really is that getting data stored is easy, but processing it is quite getting more and more the bottleneck, because the computing cannot really quick enough getting all to the petabytes in the memories. This has certain roots. One, of course, is costs. That main memory and cache is, of course, extremely costly, but also, of course, in the matter of the fact that the vendors, you know, basically there is no really big invention going on in this sense. So the memory ideas are still very similar, like have been there before. There are new concepts where we also work in Jülich here in collaboration with University of Iceland, like network attached memory, that memory is just on the network to be reused by many computing. There are things like non-volatile memory that now entered the market, so you don't have to always put it from the disk again to the main memory, so you have it already as a non-volatile entity. Still, the bottleneck exists, which is known, so to speak, as a DRAM gap. So we have to talk a little bit about it, that you understand where really the big problems in big data rely. And here's again another example of this, where you see a multi-core processor would have lots of capacity to compute, But essentially the bottleneck is here the DRAM, because there is where the data comes in. Even if you have much more multi-core processors, you also have to scale then somehow with the memory and the caches. Otherwise you have lots of cache misses. And with this, your data analysis will be also slow, no matter how many computing you apply. And that's why we call it in the moment a bottleneck. You can have much more tapes, getting petabytes stored, but getting it then quick enough to the multi-core processors, and the GPUs have actually the same problem, more or less, going through the host CPU to a GPU, a many-core processor, is also a certain bottleneck that we really can't overcome these days. And this is, of course, something which is a memory wall problem people talk about. They have talked about this in the past, but now we see it much more heavier coming. And only a smart combination and more better services on all of these different hierarchies are now the new research projects we're going in, like at Meyer, I talked in the prologue. That is a research project under the umbrella of the Euro HPC project, where we are in, and 2 PhDs of University of Iceland and Jülich engage there basically to think about with many other vendors, with many other people, how we can do there a better data management, right? It's not so much about computing. Computing is what we can do right now and can we do today because we can do it in parallel. But what are smart ways of getting the data to the computing? And this is, of course, something which is now a very hot research topic. So take away the message that this DRAM gap really exists. Could be also exam questions here and there because it's quite important. Again, the details here of this different level of caches is of course very much dependent on which system you have. Usually still it's very important to know that disks in comparison to this are incredibly slow, tapes are slow, and that of course a smart way of just increasing lots of main memory or better even caches would maybe solve some issues, but it's incredibly expensive, so nobody would really do this. In this sense, there's lots of things to be done, lots of research to be done in this area. However, there's a certain movement which makes it even more harder, and that's what I mean when I talk about storage technologies. So in the past, there was something like you have this, magnetic disk, then we had the solid state disks. We have really disk arrays in cloud data centers where just huge racks, which has nothing else than storage. And active storage, so to speak. So it's, let's say, closer to the CPU as now a tape archive, which could take lots of more data. So in a way, it's active data you can use, but still, given the fact that the storage in itself, the capacity is significantly improving. You see this in the last 30 years here. And now we have even massive more speeds. If you think about today, we're talking not even about terabytes maybe, we're talking about petabytes in research. We are already in exabyte systems and exascale. But the problem is there that it's getting, of course, cheaper with it. So people keep data. They much more accumulate data. The sensors go better. Nobody deletes data anymore because basically it is so cheap. Let's better, keep it. And in some form or another later on, we maybe reuse it or we can remove it then. And of course, this contributes to the fact that also more and more data is on these systems. And then you have, of course, this kind of peak services in clouds like Facebook, like Netflix, those Twitter, the big, let's say, players which really contribute enormously to the petabytes and exabytes that we have to deliver. So this is, of course, something where this movement has never taken place in the memory area. So there the innovation is, let's say, on a moderate pace, while storage is on an extreme fast pace, also getting more cheaper, while the main memory is still something, let's say, relatively costly today, especially if you want to have it close to the CPU. So now when you think about the costs and this big data service examples, we will have also there more details when we talk about the software as a service models. Today, you're not alone. Basically, you have cloud vendors that offer you something. And of course, I will here have different views on it. The First view I want to give you is here for research and academics. We have luckily this European Open Science Cloud, and you see that in the Science Cloud you have different, let's say, subclouds or services which are really there to help researchers to save their data. So because you can see now if you have an interesting scientific endeavor, you find a specific scientific interesting phenomena, it would be hard to delete it just because you don't know where to store it. And there are lots of momentum around this European Open Science Cloud to be used, and there are lots of funded projects in the European Commission space for research and engineering to make this happen. In a way also really funded by the momentum of the ministries of the G8, with the FAIR statement I already was alluding to, that data should be always findable, accessible, interoperable, and reusable. What all these mean, this four, will be more in detail discussed in lecture 10. But the idea is really to share the data with other researchers, to make it findable so that they can work on the data. And this is done with the European Open Science Cloud. It's not only storage, you see there's also computing, there's data management, metadata plays a big role in this, and of course networking for interconnection. And then sharing, discovery, finding those data sets is a very important part too. So the academic area, let's say, is in the moment quite well prepared for this big data. There are some interesting aspects that if you publish these days in journals or so, they require you also to provide the data. Sometimes that was not the case. Like for instance, 15 years ago, you could publish in a journal about data science and you didn't have to provide your source code, you didn't have to provide your data. In the health and medicine, this was already a little bit advanced. So there you had to provide some aspects, but usually this is coming now also to many other science areas. So you always have to provide metadata. You have to provide your kind of different source codes, whatever it is, you analyze the data. And with this, of course, you have lots of additional costs, so to speak, to put all of this data, to curate the data, as we call it. So with this, there are some services under the way. As you see here, Open Telecom Cloud is one provider. You see B2Stage and B2Safe, which are both from a EUDAT, European Collaborative Data Infrastructure, formed by many HPC centers in Europe that offer then storage essentially to academic researchers in a way which you can then nicely reference. You can put the reference with a handle system inside your publication. So no matter when the data is moved to another location or so, the handle will never change. A little bit like the handle system you know from the internet, but we will discuss it also in more detail in lecture 10. So you see, science is really responding to this, but I also say that, of course, we're not really completely prepared for the square kilometer array. Having something now for your research and basically putting it there is well understood, but how to deal with 1 petabyte per 20 seconds is still something where people really think about solutions in that area. So here we have a very popular other example of a big data, let's say, aware service. I say this big data because it has really scalability inside, in a way an automatic scalability, as we will learn in lecture 8, where you have a possibility to really buy storage in Amazon. You will see in the lecture there are different types of storages. This is an object storage. You can see something, an object storage means you put data alongside some metadata in a kind of container, this bucket container. You would give it a key, a value, metadata, and perhaps say a little bit who is allowed to see it. And this is an object. And so that's how you store data. So you would go a little bit away from this file notion. And this is used more and more incredibly often in different applications around the globe. And you see here some popular ones are Expedia, Airbnb, Netflix. These are just examples of companies that take heavily advantage of this S3 Amazon Web Service. Even if you don't know that, if you Netflix watching movies, if you having your profile, adjusted, if you do a like, if you put it on your follow list, whatever, you never know that in the back there are these systems, right, that actually delivering scalable. Because if you remember, Netflix was also starting sometime, right? It wasn't there, so it started very much in an exponential scale then, of course, with the number of users. So you need an infrastructure, again, that is scalable. And that is what Amazon with S3 can deliver. Also, you have to have good APIs, because if you want to use it out of your application, you need good APIs to really get data in and out. What was first with, the SOAP, the Simple Object Access Protocol, more and more these days is really the REST services that are getting known and used. Security plays a role. Amazon, you will find, is particularly well secured. You can make it extremely secure if you want. Usually, given that Amazon has data centers around the globe and they have a smart strategy we will discuss in one of our lecture about basically putting the data several times redundantly, they can deliver to you a durable storage which would never fail, essentially, or which would be, even if a whole data center would burn down, which is very unlikely today, you would still have the data available on another data center because some things are mirrored. So you would have your data almost to 99.9 availability. And usually this S3 is now really getting to a standard or a de facto standard. Because it's from a vendor, it cannot be directly a standard. So I would call it rather a de facto standard, where other vendors have started to put on their storage an S3 interface so that you can move data more easily from the application away from Amazon and then to the other cloud service. So it's an easy migration. Of course, this goes vice versa from other cloud vendors as well. More details on lecture 8, just to show you that, of course, this is something where the commercial cloud providers would have also good ideas how to handle big data. That's not a problem. But also, if you would now face Amazon and say we have 1 petabyte every 20 seconds coming in, they would shortly ask, how much do you have on your credit card first? And I think then they would ask, we have to go back for a couple of months to think about a strategy. So these are really orders of magnitude, which of course Amazon also not facing every day. So a solution which is often undertaken for these things is that you create so-called hybrid clouds. You will use partly open systems like AWS, like Microsoft Azure or so, and then you have your own cloud within the company. This is not only because maybe the data is too big or you need the capacity of the computing in Amazon. This can be also security reason. So some of the data maybe never leave the company. And those of you that are from Iceland here, you maybe know very well decode genetics. And for those that don't know, usually decode genetics don't really give data out. So you have to be inside the company to really work on the data. They don't load the data up to any public cloud, which is a good example, right, of how do you think now you have to create your own infrastructure within your house in order to make that happen. And there's a technology which is broadly used for this, which can still easily connect to Amazon, can still easily connect to Microsoft Azure, but it brings all the building blocks you need for cloud computing essentially with. And it has something like a cloud operating system notion. So you would have compute services from virtual machines over containers to specific functions that you can use. You have networking services you can basically have already at your disposal. You just need to tune to the networking situation in your company. The whole life cycle from bare metal to accelerators is there. And of course, in storage, you would have not only so-called object storage that we just discussed, so kind of this kind of bucket handle of objects, but also, of course, a traditional file or just simply block storage, where you have a certain area where you just on block have data stored without any notion of a file. So we have a whole lecture talking about this cloud operating system, but you will see that many systems today underneath will probably say based on OpenStack, or this software has been implemented using OpenStack. Not everybody uses all of the services, of course, that are there, but this is, of course, a very popular system as well. If you here and there in this lecture also see some of the notions like containers, you don't really know exactly virtual machines, don't worry. We will talk about virtual machines in lecture 4. We will talk about containers, Docker containers, Singularity, how you fool around with them with Mesos, with different technologies throughout this whole lecture, right? So all of these terms will be then at the end of the lectures then much more known to you, just as a glimpse what will coming up and how it relates to each other. Now, a very interesting lecture we will also have, which is, of course, big data in a completely different sort of view than you have seen with the kind of measurement device, right, in science, which is the large, the square kilometer rate is this large Facebook amount of users, or YouTube, or Twitter, essentially all the so-called online social networking. So this is a tremendous movement. And the interesting effect that you had with this is the enormous way how they interconnect the data. So you see that the square kilometer array, they have a interesting area of the sky. They will do interesting images, interesting analysis. But of course, and that is a little bit interconnected due to the fact that they're neighborhood locations. But here you have a completely arbitrary, so to speak, data structure, right? You never know who is knowing who likes what. So essentially, you see that here on the red thing, you have a kind of data pool or big data pot that is growing in one direction less than the other and completely unpredictable, and you have to deal with this. And Facebook is, of course, an extremely good example to quote. We will have in this lecture 14 lots of examples from Facebook where they use, for instance, 1TAO graph database to cope with these problems. And all of you, I guess the majority of you will know Facebook. I know there are always some people that don't, and they are actually not on Facebook, but they still know roughly what it is. So you have a friend of a friend that likes something, you see it. And things which are not directly affecting you, maybe in the neighborhood, still you want to know about it. And these things are not that easy to realize in that sort of scale when we talk about billions of users. And now think about the fact that we use several of these services. That gives you an interesting way of thinking about how many of these big data pots are out there. And then the interesting thing is you can link a YouTube lecture within Facebook and then, link it back to Twitter channels. These are all very much interconnected. And as I said, also the size here plays not necessarily the biggest problem for Facebook, right? They have lots of money. We will also explore in lecture 14 how they make money. I will talk about a bit about AdSense, AdWords, how you do this when you're interested. And I will have a couple of slides about this from a practical experience, how that works and how Facebook makes money. So this is a company that have, let's say, enormous amount of money, but here we talk about technology. We need certain new technologies like a very good graph database, but also other indexing strategies to find, let's say, old posts that you had done in 2 years ago. If you search for it and suddenly it pops up maybe in 3 hours, you're simply not interested. Or if you see a like in 3 hours from someone, you're also not interested to use Facebook. You want to see more or less an interactive usage behavior. And this is, of course, now a challenge which is rooted by the fact that there are lots of different technologies that need to work together, not only a graph database. And Facebook is, of course, a very interesting company to analyze there in detail. And I can also say that Facebook engineering is quite open. They publish every now and then. Similar like Google. For some of you that know, Google has published a MapReduce, for instance, at some certain time in the past. That is actually now more or less 16 years ago, but had done lots of tremendous movement in science to work on new solutions for big data. So all of this is, of course, underpinned by some form of a network. And now you would think about one key question. If you have something like Facebook, if you are, Zuckerberg, you will ask yourself, does it really make sense to transfer terabytes and petabytes again and again for applications? And I think all of you could matter and could, reason about this and could think about and come to the conclusion that probably that's not the way to go. Even if you have high bandwidth networking, transferring petabytes is still and terabytes when you are a big company, quite a significant challenge, especially if you do it many times often, to put it maybe to a high performance computing device, to a cloud, again and again. So there's a sort of movement that was initiated then by this so-called MapReduce, which was initially really a Google paper in 2004, as I mentioned, saying, why not we do more data locality? So saying that the jobs should be more running to the data, and the data should be close to large computing entities. And this was a big movement that's really underpinned also lots of cloud movements. And of course, Google had very good applications to show that it really works. And with this, there was a big new rise of a terminology called big data analytics. And of course, data analysis has been there since, 20, 30, 40 years. So if it goes back, of course, to history, to even Da Vinci that has analyzed data. And often what you found there is really the search for causality. So people really wanted to know why things are happening. In the big ocean of the data, they wanted to know why. Even if for Da Vinci and for others, maybe the world was flat and not a ball, still you want to know why. Now, what big data analytics actually a little bit changed in that was lots of things are correlation now. And you see that, for instance, in the Facebook ads. So some of them, the most of them are maybe very good for you. The ads are to the point. They analyzed you and say, we know your personality better than yourself, but they could be still a little bit wrong, right? So it was the 10% where you think, well, red shoes, that I'm not interested in that. I don't know how you come to this. So, and it can be, rooted in some search behavior before. So the long story short means it's more a correlation aspect. There's lots of technology inside that enables results quickly, but they're never 100% necessarily. And this is really, was a movement that still saves a lot of time, because finding causality or causal reasons is very hard. So correlation had a big upper movement with big data analytics, and you see lots of frameworks today supporting this. And we will talk more about this in lecture 5 then. One example is basically here where you have to be very careful on these things in medicine, right? Where big data analytics were used by Google with another virus. It was not Corona at that time, it was a H1N1. Of the Google flu, so to speak. That was funny because they really could use their search queries around the world that have been logged to really analyze the data and to predict where basically is the flu much quicker than any government could do. But of course, then there was another paper later on saying this is all crap. For instance, you could see if you call from the East Coast to the West Coast in the US, you essentially say already that, okay, this is something which someone on the East Coast has, so I will Google it here in the West Coast to understand it. And lots of problems with the data. And we will talk also about it again when we talk about MapReduce. So take away the message, it's not that simple as it should be. There were different big data analytics frameworks which came along, which is Hadoop and Spark. We will also have dedicated lectures about it. This is really MapReduce implementations, open source, and Apache Spark takes advantage of memory, and you will use this in your assignment. And lecture 3 will also start talking much more about it, which will come next week. So the idea of MapReduce, which is underpinned by Hadoop, by this MapReduce, is really also not new. It's a divide and conquer strategy that is really traditional in software engineering. So essentially you have a certain things of keys that you can then specifically short, shuffle, and group, which makes this reduce step really much nice. And the idea of this map, short, shuffle, group, and then reduce is inherently really nicely parallelizable. You can have this extremely scalable in parallel, and Hadoop brought the application. Google brought basically the concept. So this has been adopted throughout the clouds. We will learn about it in lecture 5. And basically this has now coming to more and more innovation in newer systems. Apache Spark is kind of a complementary system which uses much more memory if you have enough memory available. In our course, we will use the HDinsight Microsoft Azure for the assignment that I will also hand out after this lecture, and we will talk about it there. But think about that it's not only basically about the I/O, about the parts of the cloud computing with the compute part, also about the file systems, where you store data, how you store data, things like this. Interesting is that they, of course, can also interconnect with different cloud vendors, with the Amazon, AWS, S3, and so forth, as we have heard already. And then what really in the big data field was a motivation then, if you see that, now we need lots of computing, And we have big data, let's analyze it. And many of the data analysis, which is more statistical data mining, machine learning strategies like classification, clustering, regression, we talked in the prologue about it, is really making use of this. And we will also talk more in detail exactly about these systems so that you know what you do in your assignment also in lecture 2 and lecture 3, respectively. But there it's really clear that without clouds, you cannot do much. And we will learn about why. And by far today, big data is used often with these different machine learning and deep learning models. So if you see it from, 10,000 feet perspective, you would be maybe interested in a classification. You would have already 2 classes of certain data available, and there's a new data item coming in, a new customer maybe. Is it this type of a customer or is it that type of a customer? Then sometimes in clustering, you would say, I have no idea. So basically, no groups exist, but through similarity measures, you could maybe form 2 clusters, and we will talk about this as well. Then regression would be one part where you want to rather have a kind of slope or a real value really behind this. So all of these we will capture in lecture 2, so bear with me. And this course is really mostly focused to come to the end of this lecture also on supervised learning. So also your first assignment will be binary classification, supervised learning to a very moderate degree. We will be not getting out as machine learning experts, but you know how to combine it in cloud computing with big data. And this is of course key how you do this. And you see here different other examples, unsupervised learning again, where you maybe want to analyze data in a way where you don't have any aspects about different classes, where you don't know, is it this or that flower, where you maybe know just from the cell distances, if it is a specific cortical region. There are different other ways to learn. Reinforcement learning is a little bit more game-like, really, let's say, learn from practice and experience and have certain feedback functions. So there are different ways of learning, but in the course, we really focus on supervised learning. And this brings me towards already to your assignment. So we will have the 3rd lecture part then today after a short break talking about it. You will use the Microsoft Azure cloud, which is also a very interesting cloud in more ways than one. You see, for instance, the HDinsight service, if you look at it, it has the tools we just described, Apache Hadoop, Apache Spark, but it's just really scratching the surface. Apache Kafka is there, HBase for databases. There are lots of different systems, and the beautiful thing is that you will also explore in your assignment is all of this is nicely usable and accessible via Jupyter and Jupyter notebooks. And how you basically do now this reasoning, and you see, okay, you have now maybe played around with Anaconda, Jupyter, as I suggested in the previous lectures. You have that on your laptop, it works well, okay. But of course, you maybe have not enough CPUs or GPUs to process something, as particularly a big deep learning network maybe. Then you have lots of memory problems. Maybe the data is really too large, right, to really look into the memory. So what you do then? And usually you have this cloud computing stepwise approach, which always is very similar. No matter to which cloud we will go in the course, the steps are almost similar. You will have some form of a subscription, a fee to pay. Of course, in the course, we are usually free. There's no payment for you, no credit card for you. We will some form of a Spark cluster, or basically in this example will be a Spark cluster, but maybe a Hadoop cluster or something else will be deployed in the cloud that you want to use. Then you use your Jupyter notebook with a certain kernel that is basically bound to this, pre-configured, of course, it's nice in the cloud. Then you create some form of a session, you work with the Jupyter notebook, you check your data set, maybe the flowers, you load that in, or the character recognition, and then you perform your data analysis, visualization, modeling, really on this Spark cluster, which just makes it very fast. And of course, you don't have any memory limits or CPU limits usually. You rather have a money limit in practical experience, right? Not so much in the academic field, but of course in business, here you have to go to your bosses and say, we need some money to process something. And at the end, of course, you want to evaluate, you want to refine your models, which also then takes another cycles, another money. Right, but this is really all I wanted to leave here on the table for you. Here is basically then another video which shows you a little bit big data analytics in banking. So if you follow the link, then this is really all for today. We have the lecture bibliography, which I would encourage you to also look ahead and explore. And I would say we again have a couple of minutes a comfort break, and then maybe start a little bit past 3 o'clock with the assignment. See you then.